I'm going live, guys. So everyone, please put a yes in the chat box if you are able to see the screen right now. And everyone has to respond, huh? Okay. So good evening to everyone, and I welcome you all in this session of gravitation that we are currently running. This is lecture number 3. And in the previous session, we have seen about the shell theorem and not specifically shell theorem. We have seen the gravitational field or gravitational acceleration, which is G, because of the when we move up from the Earth's surface and when we move dig inside the Earth's surface. So, what is the effect of the gravitational force, specifically the gravitational acceleration that we have seen in that class? And we have derived the expression of gravitational acceleration itself. So there is lot we have discussed in the previous session about the Newton's gravitation law. Now in this session also we are going to repeat the same. Firstly, we will revise that concept, variation of earth wala, due to shape of the earth and due to rotation of the earth. Okay. So we will discuss about the variation of G due to different factors, and the first factor here is shape of the earth. So specifically we know the formula of earth gravitational acceleration G is gme upon re square. In the previous session we have derived it, okay, which comes out nearly 9.8 meter per second square, approximately, not exactly, okay. And this is the gravitational field acceleration at the surface of earth at this point. But since this our earth is rotating about its own axis, due to that, when you are here, so you are a kind of non-inertial frame, okay, because this earth is rotating. Due to rotation, there is somehow centripetal forces acting mv square upon. If centripetal forces are acting, that then they will make the frame non-inertial, non-inertial, in which the Newton's laws cannot apply. Newton's laws are not valid. So if Newton's laws are not valid, how do we make the calculation? So we make the Newton's law valid here. How? Just by sitting ourselves in that frame and apply a pseudo force. Okay. Since this centripetal force acting towards the center of the earth, this pseudo force will act exactly opposite to this force. And this force is nothing but centrifugal force. Centrifugal force. Clear? Due to this centrifugal force, it is outward. When you move here, it is like this, in this way. But most of the effect of this centrifugal force you will see from this range, because here it is like this. It is like to pulling out the earth from the equator. And that is why this shape of the earth not being circular, being a oval shape. Oval shape. Okay, actually. And if it is being oval, there is a difference between these are the poles North pole and south pole, and this is the equator line. Equator line. So the radius of pole is obviously less than the radius of equator. Now, what is exactly the difference? So radius of equator is nothing but radius of pole plus 21 kilometer. So radius of equator is approximately 21 kilometer more than the radius of pole. Okay. So if you will see here, gravitational force at pole or the gravitational pull at the pole, या फिर आप कह सकते हो कि gravitational acceleration at the pole is directly proportional to 1 upon rp square, radius of the pole, and gravitational acceleration at the equator is directly proportional to the radius of equator square. We know that radius of equator is greater than the radius of pole. So if it is value is less, then the gravitation at pole is greater, and this value is more. So gravitation at E means at equator is less. So here we can say that gravitational pull or the gravitational acceleration at pole is greater than the gravitational acceleration at equator. Okay. So please do remember this. Clear? So now if this point is clear to everyone, we will elaborate one by one. Okay. But this is the first point. Second point here is due to the rotation of Earth on its own axis. So rotation की वजह से भी there is will be a change in the actual value of gravitational acceleration. Okay. Since this Earth or Earth is rotating in this manner, okay. So particle which is situated here, let's say, will also rotate in this circle, this dotted circle. So it will experience a force here. It will experience a centripetal force. Weight of this particle will act towards the Earth's surface. Weight force will always act towards the center of Earth. So this is mg, and let's say this angle is phi. Okay. So what will be this component? This component will become mg sin phi, because this angle will become 90 minus phi. Okay. And one of the component will come in this direction. Okay. Just a second. So here, this particular man is rotating within angular speed of Earth. Due to that, it will experience a force in this circle also. Okay. Which is acting outward, a centrifugal force. Centrifugal force. Okay. Which is nothing but the radius of this circle. Same as this mv square upon r, and r is this small r, or we can say it is mr omega square. Okay. Clear? This is the magnitude of centrifugal force, or you can say the centripetal force also. But centripetal force acting towards the center, and centrifugal force is acting away from the center or from the radial direction. Okay. Now we know that this is mg. This is radius of Earth from here to here, and mg force will act towards the center of Earth. Gravitational force. Okay. So here we will apply the formula. We will resolve into two components, which is mg cos phi. This is if let's say this angle is phi. लैटिट्यूड एंगल, इसे हम क्या बोलते हैं, लैटिट्यूड एंगल, द एंगल विच वी मेजर फ्रॉम द पोल, ठीक है, टू एनी पॉइंट ऑन द अर्थ सरफेस, दैट पर्टिकुलर एंगल इज लैटिट्यूड. So this is phi. If this is phi, this is also phi. Z is forming here. This will become mg cos phi, and this will become mg sin phi. ठीक है, क्लियर है? गॉट इट? किसी को कोई डाउट है यहाँ तक अभी? If anyone has any kind of doubt, you can ask right away, right now. प्रीवियस वाले केस में किसी को डाउट है? इसमें कोई डाउट है तो बताओ, फटाफट से बताओ. तो ये तो हो गया पूरा एलेबोरेशन कि कैसे ये फोर्सेस एक्ट कर. So you will see कि the force experienced by this, which is directly downward, mg cos theta, this is the weight force for this particle in this circle. तो ये कहीं ना कहीं phi की वैल्यू पे डिपेंड कर रहा है, ठीक है, which means it is getting decreased or increased, but it should only varies between 0 to 1 because cos phi की maximum value 0 to 1 हो सकती है. This phi can vary from pole to equator only. So this is mg force effectively. This is mg dash, which is the effective gravitational pull that this particular man is experiencing at this point due to the rotation of Earth. And this is nothing but mr omega square, which is the centrifugal force about this particular point. ठीक है, इस पर्टिकुलर सर्कल में अब अर्थ तो रोटेट कर ही रही है, ठीक है, तो उस अर्थ के साथ, अपनी अर्थ के साथ ये पर्टिकुलर मैन भी और जो भी ये ऑब्जेक्ट है ये भी रोटेट कर रहा है सेम वेलोसिटी से. इट इज आल्सो कंप्लीटिंग अ सर्कल, ठीक है. Damn. So now the net effective force we know is mg dash, which is nothing but the vector addition of these two. ठीक है, law of parallelogram we can apply, and it is gives us mg square whole square plus mr omega square whole square plus 2 mg into mr omega square into cos theta और cos phi. ठीक है, so from here g dash is coming out at, if you solve it down, it is coming out as g square plus g dash is coming out as g into re omega square cos square phi. And theta or phi we have taken from here, from the positive equator axis. This is the value of effect of the rotation of Earth. देखो अभी ओमेगा से रोटेट किया तो जो एक्चुअल ग्रेविटेशनल एक्सेलरेशन था उसकी वैल्यू क्या हो गई, डिक्रीज हो गई बाय दिस कंपोनेंट. ठीक है, इफ यू विल सी कि फाई की वैल्यू 90 डिग्री कर दी, फाई इज इक्वल टू 90 डिग्री, which means we are at pole, that particular man is standing on pole. So if phi is 0, g dash is equals to g only, the actual acceleration. And from the RBD concept, I have told you that if a particular object is rotating, this disk is rotating about this axis. So whatever the point lies on this axis have zero rotation effect. तो जो सेंटर पे होता है उस पर कोई इफेक्ट ही नहीं होता रोटेशन का. ठीक है, इसीलिए जो भी व्यक्ति यहाँ पे पोल पर सिचुएटेड है, जो भी ऑब्जेक्ट पोल पे सिचुएट है, वहां पर रोटेशन ऑफ अर्थ का कोई भी इफेक्ट नहीं होगा, ठीक है। अदरवाइज दिस इज द इफेक्ट, जी डैश इज इक्वल टू जी माइनस आर ई ओमेगा स्क्वायर इंटू कॉस स्क्वायर फाइव। नोट इट डाउन, it can be asked in multiple type of question, so it is important by the point of view of examination, ठीक है। So just mention the few points here. At theta is equals to 0, or we have taken it here is 5, so phi is equals to 0. We mean that pole, we mean that it is equator, इक्वेटर पे क्या है, मिनिमम एक्सेलरेशन, मिनिमम वैल्यू ऑफ एक्सेलरेशन वी विल एक्सपीरियंस, बिकॉज at equator cos square phi having maximum value. So if it is going to be, if this expression is going to be maximum, so overall value will be getting minimum, ठीक है। So at equator we have g dash is equals to g minimum, ठीक है। And at phi is equals to 90 degree, which is at pole, g dash is equals to g max, okay, clear है this one? I hope that this is clear to everyone. किसी को कोई डाउट है भाई? किसी को डाउट है? एनी डाउट? चलो, डाउट नहीं है तो अच्छी बात है, बट एटलीस्ट से यस एंड नो। चलो इस क्वेश्चन को सोल्व करते हैं। अ सैटेलाइट इज ऑर्बिटिंग, a satellite is orbiting the earth at a height of 6 r above the surface of earth, where r is the radius of earth. Then what will be the time period of another satellite at a height 2.5 r from the surface of earth, ठीक है। तो देखो ये केपलर्स लॉ पे बेस्ड क्वेश्चन है। We know that according to Kepler's law, time period of rotation is related in this way to the radius of rotation, ठीक है। So we can say that T1 by T2 whole square is equals to K1, sorry, K is always constant, so it will become R1 by R2 whole cube. Now T1 is, let's say, T for the first case, and T2 is T2 square. R1 is given as 6R initially, then R2 is given as 2.5, ठीक है। R and R will cancel out. T by T2 is equals to 6 by 2.5 raised to the power 3 by 60 upon 25, 5 से डिवाइड कर दो, 12 upon 5 raised to the power 3, 3 upon T2. So T2 here will become 5 by 12 raised to the power 3 by 2. Okay. So this would be the time of revolution of another satellite. Any doubt? बहुत easy question है, इसमें क्या डाउट है? क्लियर है? अब बात करते हैं ग्रेविटेशनल फील्ड के बारे में। देखो, टिल नाउ वी हैव डिस्कस्ड अबाउट ग्रेविटेशनल एक्सेलरेशन, एंड एक्सेलरेशन से वी मीन द चेंज ऑफ वेलोसिटी पर यूनिट टाइम। बट व्हाट डू वी मीन बाय ग्रेविटेशनल फील्ड इज दैट अ इफेक्ट, इट इज लाइक अ कमांड। सो सपोज you are a collector of some district, So that collector denotes the gravitational force. Okay. But if you charge fine, okay, if you charge fine for two villages, for one village you have charged 1000 rupees for each person, and for second village you have charged 5000 rupees for one person. So these commands that you are giving according to your power is gravitational field. Okay. So gravitational field is nothing but the command of gravitational force. Gravitational force want to pull that particular object with this much amount of force, so that command will be given to gravitational field and it will acted upon. Clear? So always remember, field is the space, okay, is the region of space where that particular physical quantity is being active. ठीक है? जैसे gravitational field में, gravitational field is that region of the space in which gravitational force is active. Clear? तो देखो, अगर मेरे पास दो पार्टिकल है m1 और m2, ठीक है, अब m1 ने m2 को फोर्स लगा के अपनी तरफ खींच लिया, द फोर्स अप्लाइड बाय m1 on m2 is f12, ठीक है, but there is no contact in between them, no contact. Then how this force is working? So to understand the nature of non-contextual forces or non-contact force, we introduce this concept of gravitational field. ठीक है? अब gravitational field का concept से this phenomena will be very easy to understand. कैसे? देखो, we have this m1 mass particle and this is m. So what we will do? M1 will create its gravitational field. M1 has created its gravitational field. Okay. This is the gravitational field, which means that region which is created by M1 in which another particle will experience attractive force, which is gravitational force. So suppose we have a particle M2 that will come to in this field. Now, this particular field will apply the force on M2. Suppose the gravitational field intensity here is I. So this I will apply the force on M2 according to IM. The magnitude of that force is nothing but I into. So in similar way, we can say that gravitational field intensity is nothing but force per unit mass. Okay? Clear? So what is the step? Step is that this particular particle applies force on M2 particle by creating its field first. So ये क्या करता है? अपनी field create करता है. This is the field, and this field will try to attract these objects because these object lies in that field only. And field से मतलब ही यही है, the region of space in which forces are acting. ठीक है? और अगर ये ग्रेविटेशनल फील्ड की जगह इलेक्ट्रोस्टैटिक फील्ड होती, तो रीजन ऑफ दैट फील्ड इन विच इलेक्ट्रिक चार्जेस आर देयर, इलेक्ट्रिकल फोर्सेस आर देयर. ठीक. So that is the actual meaning of field. So here if you will see that the gravitational field of is given by force per unit mass. ठीक है? If this mass is of unity, mass is having one value, one. So what you will get is nothing but F. So we can also define gravitational field in that way. A gravitational field is that value of force which pulls a particle of unit mass. Okay? A particle of unit mass. So gravitational field is that amount of force which applies on a unit test mass. अब unit test mass क्या होता है? अब देखो, अगर मेरे पास दो मास पार्टिकल, M1 और M2 अगेन। सो M1 भी अपनी एक फील्ड बनाएगा, M2 भी अपनी एक फील्ड बनाएगा। तो वट एवर द पॉइंट, अगर मुझे इस पॉइंट पे फोर्स निकालना है तो वहां पे M2 का भी फोर्स लग रहा होगा, M1 का भी। बोथ विल अप्लाई द फोर्स, M1 will try to attract M2 and vice versa, which means M2 will also try to grab M1. So the net effective force will not be concluded over. We just wanted to know ki what is the magnitude of force that M1 has applied on him. So for that, what we will do, we will consider such a mass particle M naught which have unit mass, unit test mass, unit test mass, which means no gravitational. इसकी जो ग्रेविटेशनल फील्ड होती है अदर मास पार्टिकल के कंपैरिजन में नेग्लिजिबल। तो ये अपनी कोई फील्ड बना ही नहीं रहा। तो जब ये अपनी कोई फील्ड नहीं बना रहा, व्हेन इट इज नॉट क्रिएटिंग इट्स ऑन फील्ड, so whatever the field was there is the field created by the another particle, and which is nothing but m1। ठीक है, so always remember this unit mass test mass having negligible gravitational. Similarly, when we will jump into our 12th class and study the first chapter, and would study the first chapter, which is electrostats, in that also, in place of masses we study charges. So we will also, in that case also, we will also consider unit test charge, okay, which will not create its electric field. Here, unit test mass, which not create its gravitational field. Okay, क्योंकि gravitational field is the prime factor of force application, force applied. Okay, so these are the two types of field I have shown you. This is the radial field, which is acting radially. अब रेडियल फील्ड का मतलब क्या होगा, कोई भी मेरे पास दूसरा मास पार्टिकल यहाँ पे आया, इट विल गेटिंग अट्रैक्टेड इन द रेडियल डायरेक्शन। सो आवर अर्थ इज क्रिएटिंग अर्थ। अर्थ भी तो यही कर रही है, ये अर्थ है हर पार्टिकल को कहाँ अपने सेंटर की तरफ खींचना चाहती है, ट्राई टू अट्रैक्ट ईच एंड एवरी पार्टिकल टुवर्ड्स इट्स सेंटर। सो दैट इज व्हाई द फील्ड ऑफ अर्थ इज रेडियल। क्लियर? दिस पर्टिकुलर फील्ड इज ऑफ यूनिफॉर्म फील्ड। ये कौन सी फील्ड है? यूनिफॉर्म, इक्वल लेंथ, इक्वल मैग्नीट्यूड। ओके, क्लियर है? So I think you are clear with the concept of field. And if you will elaborate it, na, this is nothing but the gravitational acceleration itself. Now, gravitational field due to point mass. This we will discuss. Point mass से gravitational field कैसे? ये अपना एक point mass है of magnitude m1, m, capital M. So I wanted to know what is the force applied by this this mass particle at this point P. So for that, I do not want to disturb the field created by capital M. So which mass particle I have to put it here? I have to put here so that the field will not get distorted. Tell me in the chat box. Chat box में बताओ कि which mass particle I will put at this point P so that the field created by this point mass, capital M point mass, will not getting disturbed. तो ऐसा कब हो सकता है? When it will possible? जो दूसरा जो दूसरा मास पार्टिकल मैं लेके आ रहा हूं, which has negligible gravitational field, और negligible gravitational field किसके पास है? Which particle has the negligible gravitational field? Everyone. In the previous slide we have just seen it. देखो, which particle has no gravitational field? Which is unit test mass. Very good, Dhruvi. Very good, Priyadarshini. So I have to put a unit mass, unit test mass, unit test mass. ठीक है, m naught. Now, can anyone tell me what is the force experienced by this m naught? Let's say the distance between them is r, center to center. So what is the force applied by m on m naught? Which is g m1 m2 upon r square. ठीक है? R cap, if I want to write into the vector form, because gravitational force is always attractive, so that is why it is being negative. F is equals to minus g m1 m2 upon r square r cap. R cap is the direction vector, because gravitational force is always acted towards the line joining the center of these two mass particles, any two mass particles. Okay, so that is why this gravitational force is also termed as a central force. So Fg is a central force also. ये नोट कर लेना. ओके, अब देखो F इज इक्वल्स टू माइनस जी कैपिटल M into m naught divided by r square r cap. Now, if I divide this magnitude of force with m naught, which is of unit test mass, what I will get here is minus g capital M upon r square r cap, and this is nothing but gravitational field intensity. Gravitational field intensity. Okay. The intensity, the impact of the gravitational field which is created by a mass particle, that we have discussed in the previous slide. Okay. This is valid for all the type of mass particles. Clear? It is for point mass particle. Iz is equals to minus g capital M upon r square into r. ठीक है? देखो हमारा जो ग्रेविटेशनल एक्सेलरेशन आया था अर्थ से, ग्रेविटेशनल एक्सेलरेशन, वो भी तो यही था, g इज इक्वल्स टू जी एम ई अपॉन आर प्लस एच स्क्वायर. यही तो था. अगर r प्लस एच को आई विल राइट एट r स्मॉल r ओनली, so it is nothing but gravitational acceleration. So intensity of gravitational field is measured in the terms of gravitational acceleration. ठीक है? But it is different for different mass particles. For Earth, it is different. For Sun, it will be different. For Pluto, it will be different. For Mars, it will be different from each and every individual. ठीक है? Clear है? Now, shell theorem we will talk about. And when you get to know about this shell theorem, you will have a clear idea that how we have calculated the gravitational acceleration at a depth d. ठीक है? सो अगर किसी को उस पॉइंट में, उस कॉन्सेप्ट में कोई प्रॉब्लम होगी, इट विल बी क्लैरिफाई इन दिस पॉइंट. सो शेल थ्योरम सेज दैट व्हाट, इट्स वेरी सिंपल. इफ यू हैव अ होलो स्फीयर और सॉलिड स्फीयर, ठीक है, if you have a hollow or solid mass particle, and if the point is lies outside of, if you want to calculate the mass, sorry, the forces here, ठीक है, if you want to calculate the force at this point q, or gravitational field intensity at this point q, which is outside the sphere, either it is solid or hollow, so we can apply the formula for point mass only. What we can do, we can concentrate total charge of this, total mass of this sphere at the center of it. ठीक है? So what we can do, we can assume the total mass of the hollow sphere or solid sphere at the center of it, and then we can apply the formula to calculate gravitational field intensity if the point lies outside the sphere. Okay, so this is the first point. When a point is considered outside the hollow or solid sphere, Okay, the field intensity at that point is the same as a point charge produces it. ठीक है, तो ये टोटल कैसे रेप्लिका हो सकता है? It will be replicated at like this. This is a point charge, and we are having this point Q here, and this distance is small r1. R1. So let's say the mass of this solid sphere is capital M, or hollow sphere is capital M. So we can assume a point mass particle of capital M mass and calculate the gravitational field intensity, which is G capital M upon R1. ठीक है? So there is no difference between a point mass or a sphere if it is solid or hollow if the point lies outside the sphere. Okay, but what if the point lies inside of it and it is a hollow sphere? So when point is considered inside of the hollow spherical shell, the field intensity is zero at that point. तो अगर ये hollow sphere है, उसके अंदर एक point है at point P, we want to calculate Ig. So at point P, Ig will become zero. This is the simple case. Now you will ask that what is the gravitational field intensity for solid sphere inside the point, for an insider point. अगर यही point यहीं पे ही है and this sphere is solid, then what is the gravitational field intensity? I'll tell you. Intensity due to solid sphere. So what we have considered here, we have considered a solid sphere of radius capital R. Okay, and here this is a sphere of small r radius inside of it. Why this is? Because we have want to calculate the gravitational field intensity at point P, which lies inside this. Okay, and this is a solid sphere. So here we have combination of two spheres. देखो क्या combination है यहाँ पे? Combination यहाँ पे क्या है? एक तो मेरे पास solid sphere है of radius small r. We can break it down it like this. Small r radius का. दूसरा मेरे पास एक शेल है ऐसी, जिसकी ये वाली थिकनेस कितनी है? कैपिटल आर माइनस स्मॉल आर, और वो पॉइंट कहाँ पे है? यहाँ पे, इनसाइड द कैविटी ऑफ इट. सो इजंट इट अ होलो स्फीयर और अ थिक स्फेरिकल शेल? तो अगर ये होलो या थिक स्फेरिकल शेल है तो यहाँ ग्रेविटेशनल फील्ड इंटेंसिटी कितनी हो जाएगी? जीरो हो जाएगी. विच मीन्स द ग्रेविटेशनल फील्ड इंटेंसिटी इज ओनली प्रोड्यूस्ड बाय दिस रेडियस ऑफ स्मॉल आर, द स्फीयर ऑफ दिस स्मॉल आर रेडियस. क्लियर है सभी को? बिकॉज इसके लिए तो ये पॉइंट इनसाइड आ गया. ठीक है, एंड इट इज बिहेविंग लाइक अ एनुलर डिस्क. ये ऐसी खोखला ही तो है, ये भी अंदर से होलो है, और ये पॉइंट यहीं पे है. और होलो स्फीयर से कितना होता है भाई? होलो स्फीयर से ग्रेविटेशनल फील्ड जीरो होती है. तो यहाँ भी क्या होगा? इस पूरे पोर्शन से, इस वाले पोर्शन से जो ग्रेविटेशनल फील्ड इंटेंसिटी होगी वो क्या होगी? जीरो होगी. और ग्रेविटेशनल फील्ड इंटेंसिटी किसकी वजह से होगी? सिर्फ सिर्फ और सिर्फ इस पर्टिकुलर स्फीयर की वजह से, स्मॉल आर रेडियस. ठीक है, क्लियर है? क्लियर है सभी को? ये अच्छा कॉन्सेप्ट है. ठीक है, तो ट्राई टू बी पॉजिटिव इन दैट वे. टफ नहीं है ये, आसान है बहुत. ठीक है, अब देखो, वी नो दैट ऑन वॉल्यूम कैपिटल वी, विच इज 4/3 पाई कैपिटल आर क्यूब, द टोटल मास इज capital M distributed over the entire volume. Let's say the mass of this solid sphere is capital M. Again, we are going to use the elementary method that I have talked in the previous sessions. So for small r radius sphere, which will be having, let's say Vs 4/3 pi small r cube. तो इस पे कितना मास होगा, m/4/3 पाई कैपिटल आर क्यूब इंटू 4/3 पाई स्मॉल आर क्यूब. This will cancel out. So mass on the solid sphere of small r radius will be m upon total mass of the sphere r cube into small r, m into small r cube by capital R cube. This is the mass of small sphere. ठीक है. Now, what is the gravitational field intensity? I is equals to GME upon R square. Let's just talk about the magnitude. So I here will become G. Put the value of mass here, which is m of s 4/3 pi r cube divided by this r will also be the radius from the center to the sphere, which is small r. So it will become small r cube, small r square. The value of mass is 4/3 pi r cube into, नहीं 4/3 कहाँ पे है, sorry guys, it is only G capital M small r cube divided by capital R, and leftover is r square, so we will mention it. 2 पावर से 3, यहाँ पे 3 पावर से 2 पावर कैंसिल आउट. So Ig what we are having here is GMR upon R, which means at any inside point of a solid sphere, the gravitational field intensity varies linearly with the radial distance. Okay. So if I just draw the graph of it, if I just draw the graph between the variation of gravitational field intensity and distance from the center of the solid sphere, so it would be linear up to this point at the surface. Okay. And then when we consider a point outside the surface, it will behave like a point mass, and Ig is given as Gm upon r square, which means Ig is varying according to 1 by r square. If the distance between the point and the center of the sphere is smaller, when the point lies outside of it. So it is 1 by r square. So the variation would be like this. Okay. Clear है? This here Ig varies directly proportional to r, and for this Ig varies 1 by r. This is the point where maximum field intensity or maximum gravitational acceleration will be experienced, which is at surface 0 to capital R. Let me just, this is the value of I max, and this is the variation I. ठीक है, क्लियर है सभी को? Is it clear to everyone? So if it is a solid sphere, so from inside to outside, the gravitational field will be varies as linearly, and if the point lies outside the sphere, it will behave as a point mass. Okay, and the field that you are getting is field due to a point charge. Okay, oh sorry, point mass. क्लियर है सभी को? नाउ एक छोटा सा फॉर्मूला है, वो आप लिख लो. मे बी इट विल बी, it can be asked in MCQ type of questions directly only on the formula for NEET applicants. And for JEE applicants, this formula might be, there is some variation given in the formula and then they will say. Okay. I have launched a poll. Please mark your attendance in that poll. I am writing down the formula here. The gravitational Gravitational. Please mark your attendance in the poll. Everyone has to respond. Gravitational field intensity for uniform ring. यूनिफॉर्म रिंग। तो मेरे पास ये एक यूनिफॉर्म रिंग है, ये इसका एक्सिस है, इसकी रेडियस कैपिटल आर है, ठीक है, ये इसका एक्सिस है। यस। सो एट दिस पॉइंट, एट द एक्सिस ऑफ दिस, एंड इसका मास है कैपिटल एम, तो एट द एक्सिस ऑफ रिंग, आई जी इज नथिंग बट जी एम एक्स अपॉन आर स्क्वायर प्लस एक्स स्क्वायर रेज टू द पावर 3/2। ये आपको याद रखना है। इफ x is 0, which means we are talking about point is at center, because x कौन सी डिस्टेंस है, x डिस्टेंस ये वाली डिस्टेंस फ्रॉम द सेंटर टू द एक्सिस, ठीक है, क्लियर है। और आर स्क्वायर बाई एक्स स्क्वायर ये डिस्टेंस है, अपन यहाँ पे एक पॉइंट मास कंसिडर करेंगे, तो ये डिस्टेंस, ये आर हो गया, ये एक्स, तो दिस विल बी आर स्क्वायर प्लस एक्स स्क्वायर, ठीक है। सो इफ एक्स इज 0, विच मीन्स पॉइंट इज एट द सेंटर ऑफ दिस डिस्क, अगर सेंटर पे रख दूंगा तो एक्स विल बिकम 0, so gravitational field intensity will become 0. So gravitational field intensity at the center will become 0, ठीक है। और अगर पॉइंट सेंटर से थोड़ा सा शिफ्ट किया, थोड़ा सा, which means x is very very less than स्मॉल r, तो अगर x बहुत बहुत छोटा है स्मॉल r से, तो आर स्क्वायर प्लस एक्स स्क्वायर will result in r square only, because r square is very greater, so this ig will become gmx अपॉन आर स्क्वायर का पावर 3/2, so it will become r। एंड सपोज देखो यहां से क्वेश्चन बन सकता है, द क्वेश्चन विल बी फ्रेम इन सच अ वे दैट वी हैव अ यूनिफॉर्म रिंग ऑफ मास कैपिटल M, and there is a small mass particle present at a distance x from the center of the disk, and x is very very less than capital R. So what would be the force experienced by this x, this small m mass particle? सो इसकी ग्रेविटेशनल फील्ड इंटेंसिटी कितनी है, आई जी, तो फोर्स कितना लगेगा इस पे, स्मॉल एम, उस पार्टिकल का मास इनटू फील्ड इंटेंसिटी। अरे ये सेम है, एफ इज इक्वल टू एम जी, ठीक है ना, वही है। सो एम जी एम एक्स अपॉन आर क्यू, एंड वी नो दैट दिस इंटेंसिटी इज टुवर्ड्स द सेंटर, टुवर्ड्स द सेंटर जाएगी, ऐसे जाएगी, सो विच कैन बी ऑफ नेगेटिव इन नेचर। So here force is negatively proportional to x. So ये force मेरा कैसा होगा, the particle will do, ये नोट कर लेना पॉइंट, the particle will do, particle will do simple harmonic motion, simple harmonic motion, ठीक है। तो ये पार्टिकल कैसे जाएगा रिंग के, इस तरह से टू एंड फ्रो मोशन करेगा। अगर ये रिंग है, ऐसे मैं देख रहा हूँ रिंग को, ठीक है, देखो मेरे पास भी एक रिंग है, ये एक रिंग है ऐसी, तो पार्टिकल विल डू लाइक दिस, टू एंड फ्रो, टू एंड फ्रो, इस तरह से, ऐसे ऐसे जाएगा, ठीक है, एट द एक्सिस, कमिंग आउट एंड गोइंग, क्लियर है, ठीक है। सो आई होप दैट दिस सेशन वुड बी great use of yours, and if anyone has any kind of doubt you can ask right now, otherwise the lecture is being over. Thank you so much for being attentive and being responsive in the lecture, okay, bye bye, take care, and please mark